Moving on from carbonic acid and weak acids to strong acid sources. So there's a graphic here that you can see. It's kind of like what happened at Mount St. Helens. Again, these graphics are nice because they summarize a lot of things, but they really skip over a lot of chemistry. And for example, you see in the middle of that graphic, it said SO2. Okay, so SO2, we've talked about that, sulfur dioxide, one of the SOx, ends up becoming H2SO4, sulfuric acid. But how? It just kind of has an arrow. So I want to go into the chemistry of that a little bit more. So that's what we're going to try to do here. There's more to it than just acid going into the air, although that does sometimes happen exactly that way. The acid has to come from somewhere. So we talked about primary and secondary pollutants. So sometimes it's primary, it's just produced as an acid, or it's secondary, that it's produced, but then it becomes something else. Okay, that might not be a perfect comparison to what we did before, but that's the idea. So I want to unpack a graphic like this a little bit more, because we do more in this class than just look at graphics and arrows and the direction things are going. Okay, so there's some qualitative stuff here, and the primary thing I want to do with this one, with this video, is go through balancing redox equations. The book doesn't do a ton with that. It might do something in an appendix. OpenStax does that, so you want to really review balancing oxidation reduction. In fact, when I get to the balancing the redox ones, where I just go through some of those arrows that say this becomes this, well, how? You might want to stop the video and just see if you can balance the redox yourself. But first things first. So, strong acid sources. What's nice is it's a strong acid. We do not have to do a lot of math. So this is under number 2, strong acid sources. So in some cases, you get a strong acid like HCl. Actually, technically it's not an acid until it goes into water. If you've ever had a bottle of concentrated hydrochloric acid in a laboratory and you've had some of the fumes go into your nose, it's an unpleasant experience because when it hits your nose, might as well keep my track record perfect of looking at it, the recording. It dissociates in the presence of water into H plus and Cl minus. Now, if you don't know much chemistry, you say, well, that looks just like every other acid. No, it's not an equilibrium. It is 100% dissociation. So we don't have to do any, there's no Ka for hydrochloric acid. Some tables, you can look up hydrochloric acid. If you don't know any better, say, what's the acid dissociation constant of hydrochloric acid? It'll be infinity, because it all dissociates. So what we do, and I think this is basically 100% dissociation. It is not an equilibrium. Where did I pull this from? Yeah, so instead of molarity and things, that always dissolves, I talk about solubility. I don't think this is in the book. I just looked this up because I was curious. HCl dissolves in water a lot. A liter of water can hold 720 grams of HCl. This is called solubility, by the way. That's just what the capital S means. I think we use that somewhere later in the course at 20 degrees Celsius. So just going to introduce the concept. I'm going to go through 2 examples here. I think I have some other examples. So hydrochloric acid is one strong acid that we talk about, and that can be directly produced from volcanoes. I think that's in the graphic. It's one place where it can come from. Sulfuric acid. But we're going to unpack this. It comes from one of the SOx. And this has a solubility of 94 grams per liter. So still pretty soluble. I'm sorry, that's the wrong one. SO2 is 94 grams per liter. So, my bad. So it dissolves quite a bit. And then, so hydrochloric acid, sulfuric acid, and nitric acid. The reason I'm doing these are the three common things that we say acid rain. These are the most common ones. And that comes from our oxides of nitrogen that we call NOx. Okay, so here's what I want to do. I want to show you the redox chemistry. How do we go from here to here? And how do we go from here, using one specific example, to here? That's oxidation reduction. It's not, I don't think, part of what's done in great detail in the book. So if you think you know how to do it, once I set them up, in fact, you know what I'm going to do? I'm going to set these up side by side because they follow the same kind of pattern. I think that'll be the good way to do it. So if you need to go back and review how do you balance an oxidation reduction reaction, you might want to do that because I'm going to blast through this. But you can watch it 1,000 times until you get it, okay? And the sign, it's not a big concern, but I think it's worthwhile to understand how this works. Okay, so I'm gonna make space to try to do both of these side by side. So if you want to get these set up on your own, the first equation is going to be SO2 turning into H2SO4, leave some space on both sides of the arrow. And the second one we're going to do is NO turning into HNO3. Again, leave some space around the arrows. And I'm going to talk through the steps. I am not going to write down the steps for balancing an oxidation reduction reaction. That's a Gen Chem thing. If you need more tutoring on this, or it's been 30 years since you've had this, just ask. So this is the, what am I calling this? This is the redox chemistry of acid precipitation. Oops, precipitation. So SO2 somehow becomes H2SO4. I think this will work out okay. And let's take nitrogen monoxide, so NO, turning into HNO3. From an environmental science standpoint, this is not essential. It kind of stands to reason. Sulfuric acid has to come from somewhere, where it comes from sulfur oxides in the atmosphere that are generated either naturally or anthropogenically. Same for nitric acid, well, it has to come from oxides of nitrogen somehow. Here's the key, and this is where I think some of the practical knowledge comes into play, is what's in the atmosphere. You remember what we call this? The atmosphere is an oxidizing environment because there's a lot of oxygen. So SO2 will react with oxygen, and it's being oxidized to H2SO4. Okay, don't mean to insult your intelligence, but let's not forget the big picture here. Nitrogen monoxide will also react with oxygen. Well, you'll notice there's no hydrogen over here, so this equation's all over the map in terms of where it's done. Well, what's also produced? Water. Okay, so let's see here. SO2, okay. And all right. If you think you know your redox chemistry, stop the video. See if you can balance these two equations. The ultimate goal is to come down here and have a balanced chemical equation showing the redox chemistry of SO2 and the redox chemistry of NO2 to produce nitric acid and sulfuric acid in reverse respective order, however you want to say that. So if you think you know what you're doing, go for it. Stop the video. If you're not sure what you're doing, maybe watch one of them and then try the other one on your own. But I wouldn't just copy these down while I'm doing them. That's really not going to be helpful. Okay, so again, I'm not going to write down the steps, but depending on how you learn how to do this. So, the first thing we do is, I'll just use this one. I'm teaching what's called the half reaction method. So we split this into half reactions, one for oxidation, one for reduction. Oxidation is losing electrons, reduction is gaining, but we'll figure that out later. That's this method. If you do the oxidation number method, that's different. I'm not showing that here. So you split it into two half reactions. So in this case, let's see, I'll try to make this nice and neat. So logically, we split two reactants and two products into two half reactions. We balance the half reactions and then add them up. In fact, I think I'm going to set this up like that. Hey, look, that might actually work out nice and organized. Maybe I can even use that over there. So then, when we're done, we have an overall redox. So we balance this one, figure out which one's which, oxidation, reduction, add them together to get the overall redox. That's easy to say, but let's do this. So you have to kind of use a little bit of logic here. So SO2 is going to turn into H2SO4 because the sulfur is doing something. So SO2 going to H2SO4 is going to be one half reaction, and the other half reaction is whatever's left over. Oxygen going into water. At any point, you can identify which one's reduction, which one's half reaction. You might recognize this, go, well, this is taking in more oxygen. This is probably oxidation. This is probably reduction, but let's wait and see. Okay, how do you balance these? Step one, balance everything that's not hydrogen or oxygen. So in this case, the only thing that's not hydrogen is sulfur. One sulfur. Check, that's done. Let's see. The other thing is balance the, what's the next step? I know there's different ways of doing these. I think we balance the oxygen using, and if I make a mistake, by the way, that's okay, because it'll shake out. So the next step is to balance the oxygen using water. We have as much water, H2O, as we want. So I've got 2 oxygens here and 4 oxygens here. Yeah, that's right. So I need to add 2 more waters on this side of the equation. That's a legit move, there's plenty of water. And the last step, or second to last step, is to balance the hydrogen using H+, because these are all taking place in an acidic environment. So I've got, 4 hydrogens here, 2 hydrogens here. So I'm going to add another 2 hydrogens using H+, and I'm just going to look at my notes here, because I'd rather not make too many mistakes on a video. Okay, the last step is to make the charge equal on each side of the equation using electrons, which are negatively charged. So this side of the equation, there's no charge. In fact, some students will just go, there's no charge on anything, so 0 charge here. That has, this side of the equation has a positive 2 charge. So to make the sides equal, I have to put 2 electrons there. I want to make a point here. Both sides of the equation have to be the same charge. They don't have to be 0. In this case, it is 0. This is no charge here. Now it's no charge over here. On the second one, let's see, what do we have to do? So balance the oxygen using water. So there's 2 oxygens and 1 oxygen, so I'm just going to put another water there, and then I'm going to put 4 protons here, and that means I'm going to have to put 4 electrons on this side. That's correct. Let's identify which ones. If electrons are lost, that's oxidation. If electrons are gained, that's reduction. So an oxidation half reaction, that is now balanced. We have a reduction reaction that is now balanced. To add them overall, you add them such that the electrons cancel. This is like a battery. The electrons produced are equal to the electrons used. It's a cycle. So they have to be the same. You can't have 2 and 4. So we just do this move. We take every coefficient here and multiply by 2. The electrons then cancel, but not really cancel, they're just the same. That which is lost is gained. and bring everything down. And I like to rewrite things in the order that I was given. So the final one is going to be 2SO2 plus O2 plus 2H2O produces 2H2SO4. I think that's right. Yeah, because you're going to have 4 waters here on the left side and 2 waters on the right side down here, so that's going to cancel those 2 and leave you with 2 here. Oh, it looks like the H pluses cancel, don't they? So 4 H pluses and 4 H pluses, so okay, those cancel. So that's it. Double check it. 2 sulfurs, 4 oxygens, 8 oxygens, 10 oxygens, is that right? Oh, sorry, 4 plus 2 is 6, plus 2 more is 8 oxygens, and the hydrogens are 4 and 4. Check, yeah, that works. So, why did I do all of that? Okay. Redox chemistry is really important. Not that much for the atmosphere, but it's helpful to just say SO2 becomes H2SO4. Well, how does it do that? This. When we get to aquatic chemistry, this will also become prevalent, especially in water systems like a stream that have a lot of oxygen in them, an oxygenated aquatic environment. That's why I'm doing this now. Okay. See if you can do this one on your own. In fact, I'm going to give you the answer, then I'll go back and do the whole thing. So I came up with 4NO plus 3O2 plus 2H2O produces 4HNO3. I think that's right. Okay, so stop the video at any point. So there's your answer. See if you can go back through and do everything. And if you want to stop the video, cool. If you just want to keep listening, but you want to test yourself here. I'm just going to go through this kind of quickly. So, you'll have, I'm not sure which one's which. So we have 1/2 reaction, the other half reaction. So NO goes to HNO3, O2 goes to H2O. Oh, guess what? That's going to be the exact same equation, isn't it? So this is always going to be reduction. Isn't that nice? That's why we look at chemistry as a tool. Oxygen being reduced to water, very common in any system. That's why a lot of the books don't even talk about it. It's like, well, it's just oxygen going to water. The real important chemistry is the oxidation of a pollutant, in this case, into something acidic, nitric acid. So I'm not going to redo this one. So it's 4 electrons plus oxygen plus 4 H plus. Make sure I copied that down right. I wrote down a different order on my paper, but it doesn't matter. 2 waters. Yeah, it's the same thing. Yeah, so these are the same. Because they have to be. Okay. So the last one is just the specific oxidation reaction. Okay. And I came up with, let's see, 3 oxygens, 1 oxygen, so we have to put 2 waters, plus, I almost wrote 4 H pluses over here. There's already an H there. So plus 3 H plus. No charge here. Okay, let me just put, if you've done redox reactions before, these ones are pretty easy based on some of the crazy ones you might have seen in the past. So how do we balance 3 electrons being produced and 4 electrons being consumed? Well, we have to use the least common multiple of 12. So we're going to multiply the first one by 4, the second one by 3, and I'm going to let you deduce the rest of it. Because the electrons have to cancel. So 12 electrons will cancel, bring everything else down, reduce whatever needs to be reduced, and that should be your answer. Cool. Yeah, there's one on it. I'm not going to do this one. I just put this as a last example. I didn't think I might have put this on the homework. So that's 1, 2, and I'm not doing this one. This is just another example of redox chemistry. Well, actually, this is not particularly difficult. I didn't know this. I read this in the book. Solid sulfur comes from a lot of different places. In fact, we talked about where solid sulfur comes from, I think from leftover coal processing and metallurgy plants. So if you have sulfur in its elemental state, and one place your book mentioned this is in dry, sounds like an oxymoron, wetlands, there's a lot of this. If that burns or just combines with oxygen, well, you get sulfur dioxide. That's about as easy of an equation to balance. That is technically redox, but we don't need a fancy equation to do it, or a procedure. But once you get SO2, now we put it into the cycle where it can become sulfuric acid using the redox chemistry there. Okay, so let's just stop the video here and we'll pick up with the last major lesson of this chapter, and that's soil neutralization and a couple of odds and ends. Okay, good.